Hello everyone. So today we're going to find the double integral of the following integrand, cosine of quantity x minus 4y times quantity x plus y dA, where d is the region bounded by 1 less than or equal to x plus y less than or equal to 4, and 1 less than or equal to x minus 4y less than or equal to 2. So that region that we're looking at is, let me highlight it, is what you see over here. Okay. Now if I were to try to set up this integral, it'd be somewhat complicated. Looks like we might need like a couple integrals, a couple double integrals at least. It could be 3, could be more. I'm not exactly sure. Even so, even if we did set it up, the integral, it's the integrand itself, the cosine of x minus 4y x plus y. Yeah, how would we integrate that with respect to x and y here? Well, that can be complicated as well. So don't get me wrong, I'm not saying it's not doable, it's just that it's complicated. And what I'd like to do is use this idea, which is perhaps we can work with a simpler region and a simpler integrand to find the value of this integral. And the way to do that is via, call a linear transformation here. I won't get into the specifics, but the idea is this. You're going to take a region in some other axis, in this case is going to be the UV plane, and you're going to transform it to the region that you see here. So a lot of people think it's actually going backwards, that you take the region here and you go this way. Here is the theory behind that. Sorry, we're not going to go over the theory behind that, but if you look at the theory, it's asking us to do the opposite. So that's what we want to do. We take that simple region in the UV plane, so a rectangle, a square, and the idea is that this transformation will make it look like what you see over here in the XY plane. So at the end of the day, we want to integrate over something simple. So the idea here is, in terms of the concept we're going to use in the computation, let T be a transformation from a region D star in the UV plane to D in the XY plane. And this is what we have. The double integral of f of x, y dAs over D, the region D, is equal to the double integral of f of x of UB, y of UB, times the determinant of, times the absolute value of the determinant of J dA, where the determinant J is, J is the actual, what we call the Jacobian, okay? And the Jacobian basically is the partial derivatives with respect to our independent variables u and v of our dependent variables x and y. So we create these functions here, and with these, and yeah, that's the linear transformation. And with this linear transformation, the x and the y are equal to something in terms of two other variables, u and v, okay? Now, how do I go about doing this? How does this work? Let's go back to what we were looking at in terms of the region. We had 1 was less than or equal to x plus y less than or equal to 4, and x minus 4y between 1 and 2 here. And here's what I'm going to do. If I let x plus y equal u, this is like saying u is between 1 and 4. And if I let v equal x minus 4y, this is like saying v is between 1 and 2. And if I were to make up a region here, v and u with my axis, this would basically give you a little box to work with, okay? A little rectangle. Here's 1, here's 2. Sorry, not drawn out the scale here, obviously, and here's 1 and 4. And yeah, equivalently, we could look at it that way. And well, yeah, u would have to equal the x plus y, v equals the x minus y, as you can see here. But my intent, based on the notation that you saw up here, was to solve for x and y in terms of u and v, okay? So by the elimination method is what I used here. So that's when you multiply two equations by a constant or just one constant, you add them together, you get rid of one of the variables. By the elimination method, this is what you get here. And the way this works is your J of UV would equal it's a matrix, and it's equal to the partial derivatives of respect to u. That's like my first column, so that's gonna be 4/5 and 1/5. And then my second column is respect to v, 1/5 and minus 1/5 right here. And then we're gonna take the determinant of that. So yeah, it's a determinant of a 2x2 matrix, and that'll give you a minus 4/25 minus 1/25. So it's minus 5/25 or minus 1/5. Well, we take the absolute value of that, okay? And the way this integral is going to work is that integral of cosine of x minus 4y times x plus y dA over d here is going to equal the following integral. We called x minus 4y v, and we called u x plus y, so this would be cosine of v times u. And then specifically with my limits of integration here, my v's went from 1 to 2, and then my u went from 1 to 4. And then I have the 1/5 from the determinant of the Jacobian. Okay. So this is what you would get, and essentially you would just try, this is now pretty easily computable, because this would be dA is dv du, or du dv, really doesn't matter. But this integral is, not too bad, okay? So I'll leave it there, but that's how you would compute a rather complicated integral. Is you might consider doing a change of variables, okay, with the Jacobian. And in fact, if you've done a change into polar coordinates, and also with 3 dimensions, with like cylindrical and spherical, those are actually types of change of variables, okay? Those are special cases of what we just did here, okay? So I hope this helps. Thank you for your time.